two conditions, two things that are happening when I drop a ball. The gravity is doing positive work because the force and the displacement same direction. So we know that when force and displacement same direction, you're going to have positive work. That's from first principles. We also notice at the same time that as the work done by gravity is positive, the change in potential energy will be negative. So in conclusion, we can say one powerful thing. So that doesn't happen again. Yeah, things happen. But anyway, in conclusion, the work done by gravity is equal to the negative change of potential energy. Now I'll summarize this in equation form. So that's the concept behind it, but the equation that relates this, the work done by gravity is equal to negative delta PE, gravitational potential energy. So that's what we see in a situation when we drop a ball. And obviously, if we raise the ball up into the air, the work done by gravity will be negative because force of gravity will be down and the displacement will be up. So the work done by gravity will be negative because force and displacement are in opposite directions. And then as we do that, the potential energy increases. So if the ground is 0 and we raise the ball up into the air, we're increasing potential. But if we let the ball drop to the ground, we're losing potential energy, as we see here in this equation before us. So this is a situation where objects are falling down. And another situation would be if we're raising it up into the air. So in this first case, I'm dropping. In the second case, I'm lifting it up or rising it up into the air. But as long as I keep the 2 points the same, the energy in falling and rising will be also the same. So as long as I go between 0 and 10, 10 to 0, it's always going to be the same amount of energy. So this is where we're going to start with. The work done by gravity is equal to negative change of potential energy. So we also know from first principles the work done by gravity is equal to change in kinetic energy. That's from the work kinetic energy theorem that we have been looking at sometime before. So this equation here up top, we're relating the work done by gravity in terms of potential energy. We can set these two guys equal to each other because they're both equations for the work done by gravity, if you will. And the reason why we can say this is because as soon as I let the object fall, the potential energy becomes kinetic because it starts to move in the, by the force of gravity. Gravity is going to pull the object down. It's going to cause it to change from potential energy to kinetic energy. It's going to go from rest to moving through the air. So both of these guys are actually equal to each other because they're both forms of the same type of work. Work done by gravity, change in kinetic energy, which is also equal to negative change of potential energy. So now what can we say with these two? What we can do at this point is to break these two terms down in their basic form. So change in kinetic energy is going to be, well, before I do that, so those are equal. So what I can do is I can add both of these terms, to the same side. And if I do that, that's going to be equal to 0 because now I just moved this guy to the left side. It doesn't really matter. But when I do that, there's nothing left on this side. So the change in kinetic energy plus the change in gravitational potential energy is equal to 0. Now I'm going to expand this into their basic forms. Change in kinetic energy is going to be final minus initial kinetic. And then gravitational is going to be final minus initial equals 0. So anytime you have a delta anything, you're going to be final minus initial. Delta x, delta y, delta v, in this case, delta ke, and delta pe. So further expanding this, we know the equation for kinetic energy is 1/2 mv squared. So the kinetic energy final will be 1/2 mv final squared minus 1/2 m the initial squared. Potential energy, the basic form is mgh. So potential energy final will be mgh final, mgh initial equals 0. So we have two terms here. We have initial terms and we have final terms. So let's combine like terms, put one on one side and the other on the other side. And as we do so, we have 1/2 mv final squared, mgh final equals 1/2 mvi squared. Because all I'm doing here is I'm taking this term, the initial terms, and putting them on one side, and I'm keeping the final terms on the other. So 1/2 mvi squared plus mgh initial. So what we see here is that there's a type of energy in the beginning that's equal to the same energy in the end. So we can say that the final kinetic energy, Ke final, which is here, plus the final potential energy is going to be equal to the initial kinetic energy plus the initial potential energy. And so this equation here, these two terms essentially, are what we call the conservation or saving energy between the same 2 points. So again, I'm going to go back to my example where I have the ball in the air and it's falling down to the ground. Whether I drop the ball or raise it up into the air, as long as I maintain these 2 points, whether it's 10, 100, whatever, the energy between these 2 points, whether rising or falling, is going to be equal to each other. The initial kinetic energy that I had, initial kinetic energy plus the initial potential energy at the top will be equal to the stuff at the end. We know when the ball is at 10 meters, all of the energy is potential. It's not moving, it's at rest. So the initial potential energy we can calculate, we calculated that to be 196 joules. We know at the same time that the initial kinetic energy will be 0 because it's not moving. Whereas it'll be a different case in the final case, in the end here, once the ball hits the ground, all of that potential converts exactly into kinetic, because at the ground the potential energy is equal to 0. We just saw that before when we calculated the potential energy at the top, which is 196 joules. We did that in the beginning, and then at the end it's equal to 0. So all of the energy that we had in the beginning is all of the potential energy that we had at the beginning is going to get converted exactly to kinetic energy because it's going to hit the ground with a speed. So we're going to have 196 at the top and we're going to have 196 at the bottom. Even if we had both types of energy in the beginning, the sum of those energies will be equal to, will be the same in the end by this equation that we have. So what we just did there is we derived the equation for the law of conservation of energy. The energy in the beginning, the initial terms, is equal to the stuff in the end. I'm just going to rewrite it in a conventional form. KEI plus PEI equals KE final. Energy before is equal to energy after. We have saved it. We haven't moved our positions, but even if we do, it's going to be the same amount of energy. Well, it's going to be a different number, because if we change our height, if we go even higher, then the energy in that system is going to be higher than at h equals 10 meters. But this concept never changes. So law of conservation of energy. So energy before is energy after. So we'll be using that in some examples as we go further. So just referencing your text, the ebook, if we go to page 86 of the ebook, which is page 257 of the text, we find out that the sum of kinetic energy and potential energy is what we refer to as mechanical energy. So the mechanical energy in the beginning, so I'll just call it ME sub I, is going to be equal to the mechanical energy in the end, ME sub F. So the equations that we see there in our text, you can at least see where they come from, and then we can do sample problems going forward. I'll stop there for a moment. Anybody need to see anything at the top or anywhere else? Any questions?
Okay. I got a lot I need to copy.
I'm sorry?
All right. Can you go to the part where it says like WG equals PNG parentheses volume, and the second equation with the rising part?
Okay.
Yeah, that part.
You distracted today?